pleased to introduce our speaker today. So that's special. Typically, these seminars are given by rotation from several of the students that are part of the group. And but today we have Professor Gabriela González, who's going to give the talk. Gabriela received her licenciado in physics from University of Córdoba. Then she did her PhD at Syracuse University, working with Peter Salson. And then she moved to a postdoctoral position for a few years at MIT, working with Ray Weiss, you know, the guy that won Nobel Prize in physics. She's currently a professor of physics at Louisiana State University, and she was the spokesperson of the LIGO Scientific Collaboration at the time of the announcement, and so that means a lot of people all over the world knows her very well. But she also has been elected to the National Academy of Sciences here in the United States, which is very, very high honor. And we're very happy to have her here.
Thank you. Something Mario did not mention is that he was my undergraduate advisor when I did my thesis, my undergraduate thesis in Córdoba. So you have an advisor that has a lot of experience. Okay, it's very nice to be here. Sorry we couldn't be here earlier yesterday for you to hear the more fun talk about the history or the soap opera of LIGO. Today, it's a bit awkward to give a talk on gravitational wave astronomy here in the Center for Gravitational Wave Astronomy, but I hope I can put it all together and tell you a few new things. But Mario told me to do this at a colloquium level, so I'll start in the beginning, and that is with Einstein's theory of gravity. I am not going to teach you GR, it's a difficult course, but the idea is very simple. The idea is that space-time, instead of being just a rigid grid that measures distances and times, it's a curved grid. It's curved because of masses. So masses curve the space-time, and that is what then makes other masses move in that curved space-time. So these masses are each seeing the curvature produced by the other mass, and that's what makes them move. And when they move, they are also curving the space-time. So there are two things in here. It's the curvature of the space-time is what explains how masses move. But the fact that masses are moving are distorting the space-time, and those are the gravitational waves. Now the concept is simple, the math is very hard, and solutions are actually very, very difficult to get. In fact, it wasn't until 2005 that there were numerical solutions to Einstein's equations in what was supposed to be one of the simplest cases of two black holes. If you have neutron stars or regular stars, then you have to put atoms, you have to put radiation, you have to put dynamics, it's a big mess. But if you have black holes, then it's just geometry. It's just general relativity. But even then, the numerical simulations were very difficult. This is one of the first numerical simulations was done also in this center at that time. These are the two black holes. They are orbiting around each other. Newton would have said that. But Einstein's theory says that there are these gravitational waves carrying energy away and making the masses get closer and closer. That's a qualitatively different prediction than Newton's prediction. And as they get closer, they are going to finally merge into a single black hole. The gravitational waves that are being produced in here, this is 14 milliseconds before the merger, the movie slows down. The black holes are actually orbiting at half the speed of light at this time, so things begin happening faster. But they end in a single black hole with a very complicated disturbance of space-time very near the black holes, but far away, and this was actually a surprise, far away, when we are, for example, far from the black holes, what we measure are distortions of space-time that in the beginning are just like sinusoidal waves. Those are the ones produced by the two black holes orbiting around each other. The way we imagine those are distances here getting longer and shorter, longer and shorter. That's the effect right here. Not just distances, times 2, but it's easier to think about distances. So there are these sinusoidal waves, but as the black holes get closer and closer, then the waves increase in amplitude, increase in frequency, and this was the big surprise, that when they merge, the waveform was not complicated. We had been drawing these, imagining what it would look like, and we made all sorts of crazy drawings in here. And the numerical waveform, computers proved that actually the waveform that we had to expect was very simple. It took a lot of computing, but of course it's a bit more complicated if the black holes are spinning, if the masses are very different, but for the generic case it looked simple enough. And that is what we saw on September 15, 2015. This was just so amazingly close to that numerical simulation that we could not believe it. I don't know where did you first hear about this? Can you tell me? Some of you were probably at school. Did you hear in school about this? It was big news. It was big news not just in the scientific world that we expected it to be, but it was big news in the newspapers. It was front page. In Baton Rouge, we were very, very happy. We were very proud because the candidate then, Donald Trump, had been visiting Baton Rouge the same day we made the announcement, and the next day, the front page of the paper had the LIGO discovery on the front, on the above the fold, and Trump visited below the fold. But again, what is it that we saw? We saw signals, and I'm going to tell you a bit more about how we detect these signals, but there are signals on photodiodes from these interferometric detectors, the LIGO detectors that I'm going to describe to you. And what we saw is that in one of these detectors, which is the blue one, the one in Louisiana, we saw, in general, what we see is noise, but then we saw this sine wave that increased in amplitude and frequency and decayed again to the noise. And then in another photodiode, 3,000 kilometers away in Hanford, Washington, there was this orange signal that was almost exactly the same, except for the noise. Of course, these two signals have noise in there, but 7 milliseconds shifted. We had to shift one with respect to the other by 7 milliseconds to make them coincide. Yes? Is that a question?
Oh no, they just muted. Did someone join? Yeah, someone
Okay.
joined.
Okay. By the way, if you have any questions, please interrupt me during the talk. Don't wait until the end. By the end, you probably will forget the question. It's important that you ask it when you have. Anyway, this is what we saw. We're going to go back to these these waves, but just to tell you first, this is when I say LIGO detectors, these are the 2 LIGO detectors in the U.S. In Louisiana, very close to Baton Rouge, where I live, my favorite one, of course. Carla spends a lot of time in there too. And Hanford, Washington, in Washington State. These are 3,000 kilometers away. They are essentially Michelson interferometers, but 4 kilometers long. So if you go to Google Maps and search for LIGO, you can see how long they are. They are actually very, very easy to see in Google Maps. But they are not the only ones. In Europe, there are 2. A short one that we use for mostly for technology demonstration. A short one means 600 meters, which is still very long, but it's not long enough to make to be very sensitive. We need kilometer-long detectors to have enough sensitivity to make these detections. And Virgo, a 3-kilometer detector in Italy. Cagra is a 3-kilometer detector in Japan that has not been operational yet, but it's getting there. And there's an observatory beginning to be built in India. So this is a worldwide enterprise that started quite a long time ago. The concepts, both in Europe and in the US, started in the 70s. In the 80s, people began proposing again in Europe and in the US, to funding agencies building these detectors. In the 90s, there was funding approved in Europe and in the US to build these detectors, but to build what was called the initial generation of detectors. That was detectors that were kilometers long, but would probably not have the sensitivity yet to make detections of gravitational waves. And the way we describe, or we like describing the sensitivity of these detectors, is with a plot that shows the noise versus frequency. So this is the noise in strain, because gravitational waves are, the amplitude of gravitational waves is dimensionless. I told you that if there is a gravitational wave going through the room, distances are getting longer and shorter, but the amount of change of the distance is proportional to the distance. So the distance between the sun and the earth is changing a lot more than the distance between us. And that's why the longer the interferometers, the better, because the easier it is to measure the change in distance. That's why we need kilometer-long detectors. But when we plot the noise, what we plot is not the noise in, or the signal in the change in distance, but the gravitational wave amplitude that we call strain. So this 10 to the minus 22 means how much those 4 kilometers change divided 4 kilometers. And this noise curve is the best we got in about 2010, which was the end of what we call the initial LIGO era. So let me tell you a bit more about this. How many people have seen this plot before? Oh, okay, so I don't need to spend a lot of time on it. That's very good. Okay, so this is, again, noise versus frequency. Of course, the lower the noise, the better the sensitivity. We knew we have what we call fundamental noise limits, which is shot noise at high frequencies, seismic noise at low frequencies, thermal noise at intermediate frequencies, and again, we are going to go a bit more about that. But with this kind of noise, what kind of events can we see? Well, if we wanted to see, our target events were binary neutron star coalescences. Nobody knew, now we know a lot better, but at the time, in the 80s, in the 90s, in the 2000s, nobody really knew how many binary black hole systems were out there in the universe. People knew about black holes, not so much about black holes of the masses we can detect, which are tens to 100 solar masses. We know a lot more about the big, big black holes in the center of galaxies, but nobody knew how many were in pairs, because the way we see black holes is, of course, not from light that they emit. Black holes don't emit light. The way we see black holes is because, in general, there is another star that's orbiting around the black hole, and then we see the light or the waves from those stars, usually in the X-rays. So it is from X-ray astronomy that we know about black holes. But of course, we didn't know about binary black holes. So binary neutron stars were the target, because we know that even in our galaxy, there are several binary neutron star systems. We know they're getting closer together. The systems we know about will take a few 100 million years in merging, so we're not going to wait for those. But we know that if we can see far enough, then we will see these mergers happening in other galaxies. In our galaxy, they only happen once every 10,000 years, so we really need to see out to many, many other galaxies to see these events. So with this noise we had in 2010, we had a reach of about 20 megaparsecs for binary neutron stars. Now that's about the distance to the Virgo cluster. When people estimated how often binary neutron stars merged in that volume, that was about once every 50 years. So we took data for about a year at that sensitivity. We didn't see anything, but nobody was too surprised. But the point was that we wanted to go to the second generation to advance LIGO technology. And the way we did that is we used better seismic isolations for the mirrors in the interferometer. We used different ways of hanging the mirrors and different materials for the mirrors. So we would have reduced Brownian motion, which is the thermal motion of the mirrors that looks like a gravitational wave too, because it's like a distance change, and less quantum noise or shot noise, which is the fact that we are counting photons and there is always some quantum uncertainty in the number of not photons, so that's what we call quantum noise. And we knew how to do all of this better, so that was a design of advanced LIGO that started. Installation of the hardware started in 2010. 2013 was the first time we could make the interferometers kind of work. And then 2014, 15 was when we said, well, we are now 2-3 times better than we were before. We should begin taking data for at least a little while. And that's when the first detection really got to us. When we get to that sensitivity, to this advanced LIGO sensitivity, we will be able to see up to 200 megaparsecs away for binary neutron star systems. And in that volume, we think that there will be many coalescences per year. Now, we are not yet at that sensitivity. I'll show you exactly where we are, but that's where we are going. That is the advanced, what we call the advanced LIGO sensitivity. Now, this is advanced LIGO. I told you that the idea is just a basic Michelson interferometer. The gravitational wave is making distances change, but in a quadrupolar wave, meaning that if these distances are changing in one direction, then these distances are changing in the opposite direction. If this distance is getting shorter, then that distance is getting longer. And that's exactly what a Michelson interferometer does. But of course, we have to use a lot of tricks. We have to make the laser travel in vacuum. So there are 4 kilometers vacuum tubes, and this is ultra high vacuum. And it has developed a few leaks, but they are very, very small leaks. But we are beginning to get worried about that. It's all protected by a concrete enclosure. So if you go to Google Maps, what you see is the buildings and the concrete enclosure and the parks and the cars parked around. The mirrors are not mirrors bolted to an optical table. They are actually 40-kilogram mirrors that are hanging from glass fibers that are monolithically welded, and that is one way of avoiding or reducing the Brownian motion in the band, in the frequency band that we want. And these are hanging in quadruple pendulums. In initial LIGO, these were simple pendulums hanging from metal wires. That is how we reduce the Brownian motion and the seismic motion. A pendulum is a good seismic isolator. Do you know why? You probably have played with this, but didn't quite realize. When you play with a yo-yo or with a pendulum, you usually play like this. But if you imagine moving the yo-yo like this, the pendulum, if you move it really slowly, then the mass will move just the same as the top. If you move it at just the right or the wrong frequency, depending on what you want, what we call the resonance frequency, then the yo-yo is going to move a lot more. And that's why we call that the resonance frequency. And that frequency depends on the length of the pendulum, on the mass, on the length. But then if you move the top much faster than that natural frequency, then the bottom, the mass, moves a lot less than the top. So a pendulum at those frequencies, at frequencies above the natural frequency, is a seismic isolator because the top might be moving a lot, but the mass will be moving a lot less. And if you hang that pendulum from another pendulum, from another pendulum, from another pendulum, then it's all the better. So that's what we do. That's why this is a quadruple pendulum, and then we also have to play other tricks. All of that is not enough for seismic isolation. We have to hang that from a very complicated system, which is a seismic isolation system. These are essentially 3 layers of metal where we have lots of sensors that measure the relative motion between the layers, and then we have lots of actuators, pushers, that cancel the noise. And this is called active seismic isolation system because we measure and then we cancel it In initial LIGO, we just used layers of metal and springs between the layers, which is another way of saying pendulums. They are oscillators, and that is called the passive seismic isolation system. But this is a lot better, especially at low frequencies. Remember that's what we had there. All of that, so that's a seismic isolation, that's a quadruple pendulum, all of that is hanging inside vacuum, which means that you have to do everything right, because once you close the vacuum, you cannot do much until you discover what you did wrong, and then you have to go in there again. The laser is a high-power laser that has lots of photons, and this is proven the most difficult part to deal. And then, of course, it's not just a simple Michelson, and I'm not going into the details of this, but we use a lot of optical tricks to make the sensitivity be what we want. So we don't make the light just go from the beam splitter 4 kilometers to the end. We actually put a partially transmissive mirror in here, which makes the light go back and forth between these two mirrors. And if we keep the mirrors at just the right distance, then the light will go back and forth onto itself, and then the signal will build up. But that means that we need to push these mirrors, we need to act on these mirrors so that they are at the right distance. Those are feedback control systems, which is what makes this system very complicated. We have hundreds, somebody counted, I think thousands, but the basic one, it's hundreds of feedback systems in which we have to measure signals and control them. So we have these are called fabricator cavities, one on each arm. We make the light getting to the output. There are the two beams getting to the output. We make those beams have destructive interference, and that's because we can measure light we can measure a signal from the dark. If these two distances are the same, then we should see no light. No light means, of course, noise. We still see the quantum noise, but in principle, we see no signal at the output if these two signals are the same, but if these two distances change, then at the output is when we see the gravitational wave signal. Another thing we do is that because the two beams that get out have destructive interference, then the two beams that go back to the laser, there are two beams because the laser came here, beam this, and then the other beam came here, and then beam this. So there are two beams coming out and two beams going back to the laser. Those two beams have constructive interference. That's conservation of energy. If these two are destructive, then these two have to be constructive, which means that all of this is acting like a mirror because it's sending the light back. So we don't let it go to waste. We put another partially transmissive mirror in here, which makes the light go back and forth between the interferometer and this mirror, so we have more circulating light. So even though we may have a 20-watt laser that we had in initial LIGO, we end up having tens of kilowatts circulating. And that's how we win. This is called the power recycling technique that is essential for this technology. And we don't end there. We actually put another mirror at the output to send the signal back. We call this signal recycling mirror. And we need to play a lot of other tricks. That's why these systems take so long into design, into building, and into operating them. It's not just putting all the pieces together, it's making them like each other and work together. And that takes years. That's why we still, even though we have all the hardware for advanced LIGO, we don't yet have the sensitivity, the advanced LIGO sensitivity that we plan to have in the future. So, as you know, we discovered gravitational waves in 2015. That was right at the beginning when we were beginning to, planning to take data for just a few months without seeing anything. That was going to be just a test run, and of course it wasn't. We didn't only discover that first wave, actually we saw 3 different signals, all from mergers of black holes in the 4 months that we took data in here. We call that O1. This is the range that we had in the two detectors, the range 2 binary neutron star mergers. Remember, 200 is the number that we really want to get to. Livingston was at 60, Hanford was at 60. We went down for about a year to improve the sensitivity. We began taking data in end of November of 2016. Hanford actually was then at about 60 megaparsecs. Livingston got better to 100 megaparsecs. So again, these things we make progress, but it's slow and it's painful. But we took data, and again, we saw several more signals I'm going to tell you about. But what was even better was that by the end of this run, Virgo began taking data with us. August 1st of 2017, from August 1st to August 25th, when we ended the run, we took data with 3 observatories, not 2, which is essential for triangulating the signals that we see. And this is what we expect. I'm going to come back to this, but we have been down for a bit more than a year now, and we are beginning, I think it's next Monday, we are beginning what we call an engineering run. When we finish the calibration and do all the diagnostics of the interferometers as we have them now, and begin taking data in the 3rd observing run on April 4th, I think. So all 3 is about to start. This was our goal, 120 to 170 megaparsecs. Again, we are very proud at Livingston. We have 130 megaparsecs. We had a cake for that. At Hanford, they're still improving the sensitivity. I think they got 90. What was that? That's not the one. I know I don't have internet. I want it. Is this the one? Yeah. Okay. Sorry about that. Okay. So this is more or less how it's going to be happening. We are going to improve the sensitivity, take data, go down, improve the sensitivity a bit further. What's going to be new is that we are going to be taking data with Virgo from the beginning. So we're going to be taking data for about a year with Virgo. And by the end of it, and these are all very fuzzy boundaries, but by the end of it, Canberra might join us. So we might have 4 observatories in the network. So this is going to be a really, really exciting year. This I showed you was the sensitivity we had. In 02, we had this sensitivity, just to give you the context. So this was the 20 megaparsecs that we had with the best of initial LIGO. This is the advanced LIGO sensitivity, where we want to be. This was 02. 03, it's just a bit better actually. In the spectrum, it doesn't show very different, but in the range, it shows a lot more. Actually, let me show you that what's most important for the number for these 200 megaparsecs is the sensitivity at these frequencies. That's what will be most of the signal. This is the catalog of signals that we have detected now with LIGO and Virgo detectors. We just published this, and several of you might be authors of this paper. Mario certainly is. We have discovered in the first 2 observing run 10 different mergers of black holes. 10 is, now it's beginning to be many. It's not just one, it's not a few, it's 10. And all kinds of different properties, and as you probably remember, the best of all so far, the binary neutron star merger. And that was the last signal that we saw on August 17th. Now, of course, what's important about these detections is not just that we make nice plots. This is not the way we detect them. This is not the way we read the properties. We show the waveforms in here, but the waveforms are far from obvious in the time series. It is only obvious in the time series for that first detection. If you look at the data for all the other detections, for some of these, you might hear it if you put it on a speaker. But I, at least, don't see the signal just as clearly as we saw it for the first one. These are the detections. What's important about the detections, what's shown in here, is that we use different methods. Actually, sorry, I didn't have the list of detections. Where did they go? Okay, so this is a list of detections. We also have some marginal triggers. There's a slide missing in here with 11 detections that we saw. They were all found with at least 2 pipelines, 2 algorithms that look for those. Some of those were found by 3 different algorithms, including one that looks for unmodeled signals. So we don't even have to assume that we are looking for binary signals. But then we also have a list, we put in the trigger, a list of marginal triggers. Things that we don't know whether they are signals or not. They are probably noise. Some of these, we think that artifacts, noise can account for these. For most of the others, we don't know. But they are out there. The data is public for people to look at these. Now, when we look at the sources, and the sources are named GW for gravitational wave, and then the date. So the first one was 150914. The last one was 170823. The binary neutron star was 170817. We have lots of different properties that we can measure. The masses, these are the individual masses. We can measure a combination of masses that we call the chirp mass, and that is the parameter that we can measure with the best precision. And for the signal that has the largest signal-to-noise ratio, which is the binary neutron star, look at this precision. That is amazing. That's 0.1% precision on that chirp mass. It doesn't quite translate in the same precision for the individual masses. That's more like 10%, a few percent, depending on that.
So plus 0.001, is that like 1 standard deviation? Or?
That's a 95%, 90% credible interval. If you're interested in the details, on which I'm not the best expert, these are Bayesian estimates, and these are 90% Bayesian credible intervals for the parameters. Anyway, we can also measure a combination of spins, and I'm going to go more into that. The final mass, the final spin. Notice that the final spin is almost the same in all of these. It's 0.7, around 0.7, which is what you expect from the angular momentum that was in the system before they merged. That angular momentum of the 2 masses orbiting around each other is converted into the angular momentum, at least part of that is converted into the angular momentum of the final object, and that is measured by the spin. The units for the spin, as we put them here and here, are dimensionless because we normalize them such that spin 1 means that the horizon of this final object, or the radius of this final object, is rotating at the speed of light. So normalized that way, the maximum spin is 1 or minus 1. Of course, that indicates the direction. 0 spin means it's not rotating. So we can measure the energy that was radiated in mc squared. This is E equal mc squared. We love that formula, of course. The distance in megaparsecs. Notice the distances that we have. The closest one was that binary neutron star merger, was at only 40 megaparsecs, but the black holes, we can see them much, much farther away. This is the one that's farthest away at almost 3 gigaparsecs. The redshift, however, is kind of small. Even this one, which is the highest redshift, is 0.5. So we are still seeing the very close local universe, and only black holes. Now, of course, we make nice movies. Those tables are not the most interesting way of looking at these. So these are movies that are showing the waveform, and we can also look at the properties of these. I like to point out that the first one was special, not only because it was the first one, it is the one that has the record in the strain magnitude. It's the one one with the largest peak strain that we have detected so far. And we almost missed it because we were in an engineering run. We were not observing quite yet at the time. We were very lucky, so that had the two black holes had 29 and 36 solar masses. 3 solar masses were emitted at energy, so the final black holes had 62. It was about 1.3 billion light years away. That's 400 megaparsecs. The third one, which is the December, the Christmas one, this was December 26 UTC, December 25, it was still in the US. It had 14 and 8 solar masses, so almost a factor of 2 between the two initial black holes. That's the one that has the black holes, the initial black holes, most different. The smallest one was this one on June 8th of now 2017. That at the end had 19 solar masses, just a bit smaller than this one. But the masses were closer to each other. The largest one was this one on July 29. This one had a final mass of 80 solar masses, larger than this one, 62. This was the previous record before this one. And of course, it's also the one that we saw farthest away. We could see it because it was so big, but the signal is not strong because it's that far away, 9 billion light years away. So this is a nice catalog. Of course, we also like to put it like this, and this I think shows how much astronomy are we really doing. I mean, this is really gravitational wave astronomy now. These are the masses, the x-axis here. It does not represent anything. We are just trying to put the black hole figures not on top of each other. The only scale that matters is the vertical scale, which is the masses of the black holes. The ones that we have discovered are all binary black hole mergers, so there are the initial masses and the final mass. So you can say that these were 2 or 1 or 3, depending on how you want to count. But we have seen a lot of black holes. And if you compare with the masses of black holes that we knew from X-ray astronomy, ours seem to be a bit bigger. Of course, there are some that are of the same mass, but ours seem to be a bit bigger. That's probably because the black holes, the X-ray black holes, are a different population than the population of black holes that form binary systems. But that's what we are discovering now. This is part of doing astronomy. So I think this is very exciting. One of the things that to me is most interesting about the catalog of black holes that we have now, and with 10 you can begin to do some statistics, is that it's very difficult to measure the spin of the black holes before the merger. It's easy, relatively easy to measure the spin of the final black hole or the final object after the merger. But before the merger, it's very difficult because it has to do with measuring the modulation of the waveform, and the waveforms are very short, so it's very difficult. So the only parameter that we can kind of measure with a significant error is, now you have to stay with me, it's each black hole has a spin, and it can be in any direction. We look at the projection of these individual spins along the orbital angular momentum axis. And then we add them up. And we have gotten, of 10, 8 that are consistent with 0. Which means that either the black holes have low spin, or they are anti-aligned, or the spins are aligned along the orbit and not perpendicular to the orbit. We kind of expected, and many people expected, that big black holes like these, 10, 20 solar masses, 30 solar masses, would have spins kind of large. The X-ray black holes, there are black holes that have been measured with spins at 0.7, 0.8, 0.9. Ours, again, this particular combination is low. The only ones that are away from 0 are the December one, December 2015, and the last one, the July 28. But they are still small, they are 0.2, 1.3. So that's interesting. I don't know what it means, but we are learning about black holes. The other thing that we have measured, and I like to show it this way, these are all figures from the same paper, the catalog paper, is the chirp mass, which is this parameter that we can measure, with respect to the distance. And what we can see is that larger masses we can see farther away. But now we have kind of a distribution between masses and distance. And then you can compare that with distribution of galaxies, with distribution of other astrophysical objects, of their masses or luminosity versus distance. And that is something that, for example, can either confirm or refute this hypothesis that's floating around that maybe the black holes that we are measuring are biased by lensing. We have no way of knowing whether the images that we see are images of pure images of black hole or pure signals from black holes, or they are lensed because they are coming from far away and there's something big in the middle that made the signal here a bit larger. We see that with optical signals. We see that with a very small fraction of optical signals. So it's not natural to expect that, all of these or a large fraction of these are lensed signals, but the distribution of masses and distance could, again, confirm or refute that. The other thing that we don't do that well is localization. Localization, especially if we only had 2 detectors, when we had the 2 LIGO detectors, they look like big arcs in the sky, because the information that you have is the time difference of the signals, the arrival time difference of the signal. That's 7 milliseconds for the first one. But that only tells you, for example, if the time difference is 0, then you know that the signal, the source is somewhere in a ring in the middle between the 2 detectors. If it arrives here before than there, then there's a ring on this side, but there's a ring on the sky. Because of the phases between them and the signals, we can get a bit more information than just a ring. Of course, it's a thick ring, depending on the signal to noise, but then we can also say this side is more likely than this side, because we have more information than the time of arrival. So, localization is not very good, so calling this astronomy was a bit of a question mark until we began taking data with LIGO. If you look, there are these signals, this one, and this one, that are really well localized. Those were the signals that we saw with LIGO. Having 3 detectors allows us to triangulate, and even though these are tens of square degrees, that's a lot better than hundreds of square degrees of the sky. And in particular, this one, which was a binary neutron star merger, as you probably all know, was very important to have it localized, because then we could tell the astronomers, go and look there rather than look around there. That signal was even more exciting than that. Even before we could localize, and there were some anecdotes, I can go into the questions period on how, again, we almost missed that signal, but we didn't, is that at the time, even before we saw the signal in our data.
Excuse me, just to clarify, so this localization is improved, but can you improve it further with more detectors, or is it just, that's it, with 3 you reach the maximum and the rest is just noise?
No, you can, with 3 detectors, there are still points in the sky that you are blind to. There are points in the sky where you may not see in any of the 3 detectors. That's what we call a blind spot. There's a lot of blind spots with 2 detectors. There's still a few with 3 detectors. With 4 detectors, you don't have blind spots. Of course, you have a lot of, around the blind spot, you have a region of very poor sensitivity. So it's not just one point in the sky. It's an area in the sky that you have poor sensitivity to. So that goes away with 4 detectors. The localization is proportional to the sensitivity of the detectors. So the better the sensitivity, then the more we can shrink these. So even if you have 3 detectors, making them better and better will shrink this. But if the signal is at a blind spot, then you won't see it. So more detectors is better.
Assuming there are no black holes, and sensitivity stays the same, does any detector count?
Yes, yes, because it's not only the localization of the source. There are about 14 different parameters that the waveform has, and that is assuming that the signal, that general relativity is the right theory that predicts the signal. So, for example, the polarization of the signal has to be quadrupolar if it is a general relativity waveform. But you can test that kind of things if you have redundancy. And that's what you begin to have. We don't quite yet have with 3 detectors, but with 4 detectors and 5 detectors, we have more and more redundancy, and we can begin to test general relativity predictions. To me, I have to say that there's a much more prosaic reason for having more than 3 detectors. And it's that detectors go up and down all the time. And then if you have 4 detectors, if one goes down, you still have localization. If you have 3 detectors and one goes down, you are going back to the big ring. So to me, that's the main advantage. Anyway, I was telling you that this binary neutron star detection, even before we saw the signal in our data, we received an alert from Fermi that they had seen that this was an automatic alert. It wasn't anybody giving us a phone call, but there was a signal in the Fermi gamma ray detector saying there was a small gamma ray burst in there. And actually, let me just do one thing I forgot here. So this is the signal that we saw in our detectors that was many tens of seconds long. That's the merger time, and that's the gamma ray burst. Less than 2 seconds later. So when we saw that there was this signal in our detectors, in Hanford and Livingston, in Virgo it was not that obvious. But we knew that Virgo was working because we had seen another obvious signal before. But we had this obvious low mass pair, the first low mass pair, because the longer the signal, the lower the mass. So this was a likely neutron star merger, and there was a gamma ray burst shortly afterwards. This had to be neutron stars. And we had Virgo there, so we had localization. So we pointed astronomers, we could get from our data the low mass, the exquisite precision for the Chern mass, the distance, and that was very important. It wasn't only the localization, it was the distance. It was 40 megaparsecs away from our gravitational wave measurements. So people could go out and look for signals from relatively nearby galaxies. They could tell which regions were more likely to be in those 30 square degrees that we pointed people to, because there is a catalog of galaxies 40 megaparsecs away. So, as you probably know, we published this. It didn't appear in the front page of most papers, but, but yes, here, many of you were here in Taurus. So Taurus is part of the authorship of this paper. So this was the LSC, the LIGO and Virgo paper with the observation of the gravitational wave signal. This is the list of collaborations that looked for that counterpart, not just the signal, but the counterpart. And we have this graph that I love showing that that's a localization of the signal. This is an image of the galaxy that was identified as the host before and after on that same day. I like this signal. I put this one in here. This is the one that Taurus, the image of the same galaxy that Taurus found from the Taurus follow-up. But this is the number of wavelengths in which we have seen this signal. So we saw it in gravitational waves. We saw it for some number of seconds, tens of seconds before the merger. There was that gamma ray. There were no other gamma rays associated in the same location with that. There was the optical counterpart that was blue, but but then it didn't, and then there was a red component that wasn't that strong, but then it got stronger. So the infrared and the blue and the ultraviolet had different time dependencies, which lets us know about the structure of the neutron stars and the electromagnetic wave production, which is of course not my expertise, but it's what makes this so exciting. And what was incredible is that more than 10 days later, X-ray and radio signals began appearing from the same source. And they were there for hundreds of days. So that was amazing, and what I like the best is that NASA produced a movie about this. You might have seen this movie before, but I love showing it. This is how we reconstructed the story. The two neutron stars were orbiting around each other, producing the gravitational waves, produced the gamma ray burst, and then an anisotropic emission of electromagnetic waves, and then the shock waves that produce the X-rays and the radio. So that's the story. Like I said, it's a beautiful story, isn't it? Now, what appeared in the papers, which you might have heard, was that this explained the origin of gold, how the universe creates gold. How many of you have heard this story? I think it's one of the nicest things about this. Of course, we don't really know for sure, but the reason people talk about that is that when we think about how the elements were created, the different elements in the periodic table have different number of neutrons in the nucleus, and that's what determines what element it is, and of course the number of protons and the number of electrons and protons they have. But to make these atoms, these particles had to get together somehow. All these neutrons and protons had to get together. So how did that happen? In the very beginning, it was a soup of elementary particles after the Big Bang, and then gravity began pulling things together, and then helium and hydrogen and helium began formed, but that was about it. Things were a lot more difficult to get formed until, again, gravity took over and made stars, and in stars there were heavier elements up to iron or so, up to this row of the periodic table in the stars. But that doesn't make them here on Earth, right? I mean, there's no way I got this going to the nearest star. The way I got the gold ring is because some of those stars exploded. And when they exploded, then they sent all these elements out there, especially carbon, and that's what got to planets, to the sun like ours, but also to planets, and that's what allowed us to be out there. But we don't need gold to have in our system, right? We need carbon, and that's what makes life abundant on life. That's why Carl Sagan, I don't know how many of you remember or have heard this, say that we are all made of stardust. Because our elements, the elements that make up life, were created in these stars and then expelled in these explosions. But it turns out that gold and platinum and these precious elements are not created in the stars. At least not in regular stars. So the next theory about this was that, well, there are some stars that explode that have supernova explosions, but there are some special kind of supernova explosions in which the core actually collapses due to gravity. And that collapse, that core collapse supernova, when the core collapses, it produces heavier element than iron. So there was iron in the star, but now in the core collapse, there are heavier elements. And those supernovas also explode, and then those elements went out. But there aren't enough supernova. It was about 10, 15 years ago that people realized the gold abundances in the stars, which is not just on Earth and our sun, but in the stars in general, cannot be explained by supernovas alone. So the alternative explanation was mergers of binary neutron stars. Neutron stars are compact stars. They are also produced in these core collapse supernovas, so they have these very heavy elements in there, and when they merge, there is an explosion, and out there go these heavy elements. But nobody had seen a binary neutron stars merger yet. People suspected that the short gamma ray bursts were signatures of binary neutron star mergers. But there was no proof until now. And that is how this one observation came out in the papers explaining the origin of gold in the universe.
So it's all elements starting from gold and upwards?
Well, not from gold, of course, and there's a range in here, but the heavier elements in here at the bottom of the periodic table, these are elements that do not come from exploding white dwarfs or exploding normal stars. Okay, but apart from gold and speculations about heavy elements, there are other things that are very, very interesting that we could see with just this one observation. One of those saw that we saw the galaxy, we saw the distance at 40 megaparsecs. However, we don't really know whether it was 40 megaparsecs because we cannot measure the redshift. And the gravitational wave is affected by the expansion of the universe, just as electromagnetic light is. But we don't know what the redshift is. So those 40 megaparsecs is the apparent distance. However, if there is an optical counterpart, then there is a redshift measurement. So putting together the distance and the redshift measurement, you can measure the Hubble constant. You can measure the rate of expansion of the universe. Of course, there are actually much, much better ways of doing this. There are two different ways of doing this. One is looking at the cosmological microwave background, and the best measurement is by Planck. The other one is looking at the redshift of supernovas that are far away, and this is a group that has made the best measurement of that, and those two measurements are now more than 3 sigma apart. So these two measurements disagree with each other. And now we come with the third measurement. So who do we declare the winner? Well, we cannot quite do that because our error with this one measurement is still very large. This is our measurement of the same constant. This is our 50% and 90% interval. So, of course, we cannot decide who's right, but we will. Once we have more signals to do statistics, once we have stronger signals with better detectors, we will get there. We can measure, we can say something about the compactness of the stars. In a neutron star, the radius is not determined by the mass, like in a black hole. Depending on the equation of state, depending on what's the nuclear structure what's the structure inside the star might be smaller or bigger. And our measurements seem to say that they are kind of small. So we have begun ruling out some theories. This is our measurement, this is our 90% credible interval on the compactness of the star, and these are predictions from different theories. So we can begin ruling out theories, which I have to say for an experimentalist is one of the best things to do. We saw that there was less than a 2-second difference between the short gamma ray burst and the gravitational wave merger. That means that these two signals traveled 130 million years and arrived here only less than 2 seconds apart. So that's incredible proof with some caveats, but it's still incredible proof that gravitational waves travel at the speed of light, which is an assumption, after all, in the theory of relativity. But here, there is very, very strong evidence for that. So what's coming next? Well, I see a typo. O3, like I said, is just around the corner. We are starting next week the engineering run. We are going to start in a month the observing run. We are going to be taking data for a year. So what's happening now? Well, there's still technology development being done in labs. That's actually what we use to do all these improvements. We need labs that develop technology. This is a picture from Volker's lab here at UTRGV. This is Thomas Corbett's lab at LSU. Most of the work is happening in the control rooms. I don't know how many of you have visited the control rooms. I know at least a couple of you have. But when things happen, we are really very happy there. It's a very intense time when we look at the graphs on the screens, and we are always worrying about something happening there and fixing problems. And of course, people are testing algorithms on analyzing the data. And all of that is to discover signals and then do the follow-up. This is a picture of the observatory in Salta, in Argentina. Something I wanted to mention, and I know I'm out of time, so I'll do it really, really quickly, is that we are using now in advanced LIGO something that was not in the baseline. Sometimes the future arrives faster than we think. We are using something called squeezed vacuum to improve our sensitivity. To improve the shot noise, I told you that what we do is we just increase the power so we have more circulating photons, so we have less statistical noise in counting photons. Turns out that increasing the power has turned out to be very, very complicated. Things get hot, they deform, it's difficult to control, there are point absorbers on the mirror, so we have to find a place to put the point absorbers without doing that. Carla has to measure transfer functions and how to get the mirrors aligned when all these things are happening and mirrors are getting deformed. Another alternative is to this is the uncertainty that we have in the noise. If you have an electromagnetic wave, then there's some uncertainty in phase, that uncertainty in amplitude. So you can represent that as an uncertainty ball or an uncertainty cycle. If you turn down the amplitude of the laser to 0, then that's the vacuum uncertainty, and that's what we measure now. But it turns out that doing special tricks, we can squeeze that ball, and we can have less noise in amplitude or phase. And that's why we call it squeezing. Except that because we are looking at the destructive interference at the output, what we need to squeeze is vacuum. And that sounds like magic, but it has been done. What we do is we have a squeezed vacuum source, which just means it's a laser that we prepared in a status that is synchronized with the main laser, but we prepare a squeezed vacuum and then we turn the amplitude down, so that it is squeezed vacuum. And that is what we have used. The latest best sensitivity we've had at LIGO Livingston of about 130 megaparsecs. That was done with 40 watts of power and squeezing. So this we measure squeezing in dBs, and that's the degree of squeezing that we have. And that is how we got to 130 megaparsecs. I got a screenshot of February 28th, so that was yesterday. And in the control room, we have this plot of the last 24 hours of the sensitivity. This is in megaparsecs, the sensitivity in LIGO Livingston, in Hanford, and in Virgo. And we are all getting there. We are all ready to start with the third engineering run. So this is a very, very exciting time for you all to be doing this. Gravitational wave astronomy is really here, and this is really, really exciting. I'm very glad you're all interested in this. Thank you.
We have time for a few questions. I imagine.
Yeah, I didn't have any rush, so, and I love questions.
So there's someone. Go ahead. Who was that?
Sorry, probably it was me. Hi, I'm from, I connected through Zoom. I was wondering, can I ask a question about squeezing?
Okay.
Because I saw the picture that you showed on one of the last slides with the German title.
With the German title?
So I believe on this picture, and this is what always confuses me. So I understand why we want to use squeezed light, especially for short noise. It probably would be great, but this squeezed light is injected into interferometer. So it doesn't go to the photodiode that picks up gravitational wave signal, right? It goes inside the arms cavity through the dark port. Could you explain why?
Yes, well, I'm not sure I can explain it really well, but this is actually something that we began understanding in the 90s. Carlton Caves was the first scientist to really work hard to explain quantum noise in interferometers. And we used to, before that, we just used to say, well, it's like a Heisenberg microscope. You have this shot noise, and the noise is proportional to 1 over the square root number of photons. So you want to use more and more photons, but at some point you are limited by the radiation pressure because you have so many photons and they are pushing on the mirrors, and that's a radiation pressure noise. That affects low frequency, so you cannot do one at the price of the other. So it's a trade-off between these two things. And then we had just these two curves, one for radiation pressure noise, one for shot noise, and that was how we interpreted quantum noise. It turns out that the right way to do the quantum treatment of the light, of the coherent electromagnetic field in the interferometer, is to have this coherent state of the laser at the input, which is a perfect coherent state, and then a vacuum, a coherent vacuum state that is understood as getting into the interferometer from the output port. So you consider the interferometer as an experiment that has two inputs. One is what we call the output, but it's actually the input for vacuum, and the other, which is the input for the laser. And then you have these two quantum fields, the coherent field and the vacuum, and then you do the quantum treatment of these fields in the interferometer. There has been a lot of development since then. There has been a lot of proof, experimental proof, that this is right, that you can measure the predictions of the quantum noise as predicted by this, and there are several very interesting effects, because it's not just putting these two curves for radiation pressure and quantum and shot noise together. You have interesting things in the middle, optical springs and effects like that happen. But the point is that the treatment of the quantum noise is this vacuum coherent state going into the interferometer at what we call the output. That is what's happening in the normal case. What we do now is inject, instead of that vacuum coherent state, a vacuum squeezed state. And that is how the sensitivity improves. Does that help?
May I ask a little follow-up question? I understand this idea that, but what confuses me, so we don't have squeezed light in the dark port. So we say that we have a vacuum state entering through the dark port. And now when we add this additional laser light with squeezed quantum state, why does the quantum state that was entering dark port before disappear? Why not just adds with the squeezed light? Do you understand my question?
No, I'm not sure I followed. I'm sorry.
So it's like light superposition. If I have one laser and second laser, the total power, or depending on interference, so like if I align these two lasers together, they will add up, right? So when I have vacuum state and laser, why when I add them together, vacuum state disappears?
It doesn't disappear, it becomes squeezed. This is vacuum after all.
Yeah, but it's like if we remove this laser, vacuum state appears. If we, for example, I just block the quantum squeezed laser light, vacuum state appears immediately, right? But when I unblock it, this vacuum state disappears, and instead only squeezed light enters the dark port.
No, the vacuum coherent state is always there because we are using a coherent state at the input of the interferometer, and that's why we need to have the vacuum, the squeezed vacuum source phase correlated with the laser input. So that is what the correlation, that is perhaps what best explains what you are saying. It's not like the squeezed vacuum and the laser input to the interferometer are two independent sources. They have to be synchronized.
Okay, so it's
there is, I'm not sure you can see me, but there is a little diagram, well, I'm not sure it is here, but there is a diagram in here that says that the laser, the pump laser of the squeezed source is synchronized with the main laser source.
okay, now I understand, thank you.
Okay, good. Yes, that was a good question.
Questions here?
Yes, there was somebody else before, but question was forgotten, maybe.
I'm just curious what the overall definition of the coherent state, because I do remember the definition from Sakurai, but it was very abstract, and I could never wrap my head around like what exactly it is intuitively.
Oh, a coherent state is a state, in this case of the electromagnetic field, but in general, it's a state that has minimum uncertainty in position and momentum. If it is a particle that you are following, the trajectory of, or in this case, the amplitude and phase, if this is an electromagnetic field.
So minimum uncertainty for one of them, for either amplitude?
Well, it's a coherent state is one in which this ball has the minimum size, which is h bar, and it is related to h bar. You can squeeze it, but the volume of that ball is the minimum size that quantum allows. In general, it's bigger.
So you're always going to have Heisenberg. The idea how you exploit Heisenberg.
Yeah. So it's like Heisenberg is in general more or equal, but you can squeeze it.
Yeah, but the light from a flashlight is not a coherent source.
Yeah.
It's an electromagnetic field, but it's an electromagnetic field that has a lot larger noise than the minimum quantum noise you can have. So a coherent state is one, it's an electromagnetic field that has the minimum noise that quantum mechanics allows.
So just, sorry, but I remember the quantum field theorist telling me that the definition of the photon is that it's a coherent state of the electromagnetic field.
Oh. Well, I don't know. There are people who know about quantum mechanics better than I do. I don't think that's right. No.
Maybe I'm misinterpreting.
I think a coherent state is one in which the number of photons is probably the best defined. But maybe. I don't know. I'm looking for clues there.
And just to finish my question, I encountered an article recently while preparing for the talk that I was supposed to give. So by a guy.
I took your slot. I took your time today.
No.
Oh.
At the end of March. So the guy named Sito from Japan, and now Sito from Kyoto University, proposed a method of detecting exoplanets using gravitational waves by using the LIGO detector that is not there yet. And what he basically says that one can use like two, I think, white dwarfs it was, and the circumbinary system, and that the gravitational waves from the white dwarfs would be modulated by the presence of the planet, and that's detectable. And I was wondering if LIGO is working towards that, or is it unaccessible?
White dwarf, the frequencies are way much lower than the sensitivity
Right.
of
But
LIGO. I mean, that without even discussing the factability of what you're saying, which
No,
I
but-
understand.
yeah, but I think the point is that in principle, from the gravitational waveform, you can tell whether there's a third object. However, the precision that you need is huge, because in general, that third object would be much farther away than the distance between the two objects, and then the perturbation will be small. That is actually a question that we get asked very often. I mean, you have detected so many binary black holes. How do you know that there were not 3 black holes instead of 2? And we don't know. You cannot rule out that there was a third particle or a third system far away. Not far away, but far enough away that it, or close enough that is a three-body system. It would appear in the waveform, so that would be a way to detect a third body in the three-body system. But again, the precision that you would need is huge. We might get there. Actually, this is something that some people have made calculations about. The precision in LISA is going to be a lot larger because these are signals that you will be integrating for years. So you will have a lot more signal-to-noise ratio than we have, or that we may even have in the next 10 years in LIGO. So it's not impossible, but it's not likely, I think.
And when is LISA planned to be actually?
It has a launch date of 2034. It might happen a couple of years earlier. I think people are counting on that, but it's still 20 years from now.
Martin was,
Yeah.
you raised your hand, Martin.
I had a question regarding like if this is like the interferometer is on a dark fringe, right? It's like locked on a dark fringe, and then basically you measure deviation from the dark fringe, I guess.
Yes.
But those deviations are like extremely small, and plus you have noise. So how do you actually know that you are on the exactly dark fringe?
We are not exactly in the dark fringe. In fact, I'm not sure it's not worth going back to the interferometer value. If we were exactly in the dark fringe, we will be to first order insensitive to gravitational waves, because you would be at the bottom of the Michelson, right? So you would be insensitive. So we are just a bit. We are about a picometer away from. So we have a picometer difference between the 4 kilometers.
Does it even matter what point exactly you are?
Well, it does. I mean, there are optimal points, and we try to fine-tune that.
Pretty much
But the point is that we are not exactly in the dark fringe, but we can still tell the difference. And however, the way we look for signals, it's not just looking at the filter time series to see this wave appearing. What we do is we do matched filtering. We do several ways, several different things to look for different signals. But the best way to look for these binary systems is we know the waveform as a function of these 14 parameters. So it's a big template bank that has, I think, 200,000 waveforms for the different ranges of masses and spins that we look for. And then we match those templates with the data, and then we see whether we have a good match within 10 milliseconds, actually we use 20 milliseconds, between the two LIGO detectors and the appropriate time with Virgo, and it's the same template, and then we say we have a detection candidate, and then we go and zoom on it with more sensitive methods and parameter estimation and so on. So it is actually, algorithms have. It used to be, when sometimes I go back and read papers from the early times, you read papers from the 80s on how gravitational waves were going to be looked for in the data, and people were so naive. We were so naive. This match filtering is a technique that's very old, it's very well known, very well understood in Gaussian noise. And the noise in our detectors is far from Gaussian. So we have to do and we are still doing a lot of algorithm development to be more sensitive.
Karen, go ahead, Karen.
So I glad like LIGO and gravitational wave contributed to material science finally, right? With the elements or something like
To nuclear physics, yes.
No, this is real material science. Some elements, and so my question about basically this slide and with the time scale. I'm very curious what you have the milliseconds. When you have the two large objects and the spinning and the motion, and should be minutes or seconds at least, but in your case it's the milliseconds.
For black holes.
Yeah,
black
for
holes.
black holes.
For neutron stars, the signal is much longer. how to let it sound again. It's much, much, much longer. However, all this nuclear physics is happening right here at the end, which happens at a frequency that we are not as sensitive. So we say we are doing nuclear physics, but we don't have a lot of detail about what's happening when the nuclear physics is really important. And that's why our conclusions are kind of rough so far. But
So
they will
basically,
get better.
the first time scale which you had about milliseconds, right? 0.3 or what?
Well,
is it?
actually, I think this is more like the right time scale, right? Because
So
the way
here you have 2 seconds difference between
you have 2 seconds difference.
gravitational and
Right, and the way this is usually interpreted is that this is the time where that the merger, the energy and the collisions in the merger get to finally produce this gamma ray burst. So there are 2 seconds of difference, and actually, I think I had it in here. They even have some energy dependence. Yeah, here. So these are 2 channels in Fermi and 1 in integral. So these are 2 different satellites, and these are different energies. This is the highest energy, 100 kilo electron volts, and this is lower, and this is 10 to 50 kilo electron volts. So you see that the broadness of the signal it gets narrower at higher energies. So this is the kind of things that people are using to constrain the nuclear physics.
yeah, this is nuclear physics, but mechanically when you have the collision between 2 objects, this is in milliseconds, which shows first gravitational wave detections, right? The signal, which you have signal in the millisecond.
Well, again, that's a merger.
Yeah, that is no question about merger. How this merger is happening in the millisecond. So that is the I cannot
Well, the
understand.
merger is defined as the point at which the 2 stars collide. What you are saying is that the actual merger, which is the formation of the final object, from that point up to the point that you have a stable final object, that probably takes many seconds, maybe minutes.
Yeah, but why you didn't catch this signal?
Because it's a lot smaller. That signal would be, it would produce
So
gravitational
basically,
waves.
you want to say like you're saying like
I think. So when you have 2 masses up, when they rotate, right?
yeah.
Far apart, they don't create very strong gravitational signal, but very, very close when it starts to completely merge, only at that point you receive a gravitational signal that's strong enough to be seen by the detector. Only very, very slow.
It's not only the amplitude, it's also the frequency. The frequency
Oh,
is
so you're
much
talking
lower,
about the
it doesn't
black
get
holes,
into
not the
band of
neutron
the
stars.
detector.
Black
Both
holes.
things that you're saying are
Yes,
true.
yes,
The
yes.
frequency and the amplitude.
Yes, actually let me see if I have
Yeah,
the
if you
spectrum
go to the
somewhere
new
in
signals
here.
there.
Yeah. If you look at this spectrum,
Yeah.
you see that we have a lot of noise at low frequencies and actually quite a bit of noise at high frequencies too. These black holes have been producing gravitational waves for millions of years at a lower amplitude and at a much lower frequency. So in principle, we begin to see them not only when the amplitude is big enough, but when the frequency is large enough to be in our sensitive frequency band.
Yeah,
And
but
that is
how you
only-
know like merger is happening? So okay, you have some spinning between some radius, which is will generate this signal. But how you know like this merger is happening?
Because when we match the data to the signals, what we see, the best matches we have are for these signals that have. Sorry, that was a slide. You were
I
talking
guess
about
I get a
this.
very. Oh,
So
okay.
this is all about half a second. Some of these signals, like this one, this December signal, we saw it for about 2 seconds. Here we're only plotting the last half second or so. But when we look for a good match to the data, these are the waveforms that match the best.
So that is the time scale. I think is very important. And this will tell you something what happened there, right? And And maybe mass or maybe
That's right, that's right. But,
velocity, I don't know what.
right, but again, the way we do this is, and this is part of our fault, but people, because of the way we present the signal, because, well, I'm not wearing it today, but I have t-shirts with this gravitational wave signal. What people think is that that is what we analyze, that we look at this time series, we look at that time scale, we look at those frequencies, and that's how we know that we have two black holes merging. That is not how we do it. Even if we cannot see it, even if when you plot the noise, you don't see any sinusoidal variation, you can have a good match or a bad match, but in these cases, we have a good match to these waveforms. And that's how we know that there are gravitational waves produced by systems with these properties. So the way we know the masses is not that we say, oh, we begin to see the signal here and it stops here and we see 5 cycles. We actually tried matching 200,000 different waveforms to the data, and we found which is the one that matches the best, and then we saw that it's statistically very significant because it's the same template in both detectors or in the 3 detectors and so on.
Yeah, match you're doing with the different detectors.
Yes.
Yeah, but also that with these templates produced from the theory. So you have these theoretical templates, and that's the way she said that we can identify the particular signal that we have that has that feature that lasts so short.
However, but actually this waveform can be extended forever. Right? So we know what the waveform looks like before that, but that doesn't make the match any better or worse. The way we find the match is
I agree with the match. I am not just why is the one is the millisecond, another is the 2 second or something.
Because these black holes have smaller mass. The final black hole here is 20 solar masses. This was 60 solar masses. So this frequency is higher than this frequency. So the larger the black hole system, the larger the masses, the lower the frequency at which they coalesce, so the shorter the time they spend in our sensitive frequency band.
So larger mass, low time.
That's right, and that's why most of the time we are trying to improve our low frequency sensitivity.
And amplitude also works, right? How about amplitude?
This amplitude is a lot smaller. The masses are smaller, but in fact we had better signal to noise. Well, the one that we had the best signal to noise was from the binary neutron star merger, which is the smallest masses of all. But this one, even though it has a lower peak amplitude, it has a better signal to noise ratio than this one. But let me also say that we also look for signals with unmodeled we have methods to look for signals without using model. We call those unmodeled searches. So we look for phase correlation between the detectors. These matches, you can find it in one detector. You need the other to confirm it, but you look in the detectors separately. But you can look for transients that have phase correlation between the detectors, and several of these were found by that method. So we do have independent confirmation. We not always need to know the waveform. That's how we can also look for the unknown.
Well, I think it's getting a bit late, but so some of you might want to stay, but we want to thank our speaker and finish our session. Thank you.